Now, 3. Chapter number 2, behavioral modeling. In last chapter, we have discussed about the architecture. Architecture have three types of designing. One is the structural designing, second is the data flow designing, and third is the behavioral designing. In this chapter, we are going to study more about the behavioral designing. Now, introduction to the behavioral designing, okay, modeling design. Now, signal assessment statement, most basic form of the behavioral designing in VHDL. For example, A greater than equal to B. That means signal A will have the value of B and the assessment is greater than equal to. The symbol used for assessment is greater than equal to. The effect of this statement is that the current value of the B is assigned to the A. Okay, that means this statement will execute only whenever the signal B changes its value. The similar way, there is another example. A is greater than equal to B after the 10 nanosecond. This statement is read as follows. A get the value of B when the 10 nanoseconds of time has been elapsed. That means after the 10 nanoseconds, A will have the value of B. Both preceding statement, that means this statement and this statements, are the co-current signals statements, and these types of statements are called co-current signals statement. Okay, now for a simple AND gate operation, we have program entity start with the keyword entity named as AND2, is using a port, okay, A and B as an input bit, C as output bit, and the entity named by the AND2 architecture. Now for this entity, we start architecture, and this architecture is in a behavioral modeling style. Now architecture named by AND to behave. Architecture start with the keyword architecture, and the name of this architecture is AND to behave of entity AND2. This is the name of entity is begin. Now what is the co-kernel statement for this architecture is C, that is the output bit, have assigned greater than equal to the value of A and logically R with the value of B after 5 nanosecond. Okay, now you can see this is the AND gate logic, and we will end the architecture and name of architecture is AND to behave, that we use at the end to show that architecture has been ended. Now in the AND gate, as we know, input A and B and C is the output, figure shows you. Now these AND gate will assign, like the entity design describe the port of AND to gate, and these are the two inputs A and B as well as the output C. Now architecture and behave for the entity to contain one co-current signal assessment. Now this co-current signal assessment actually show the behavior modeling of that architecture, the style of behavioral modeling. One more example is for the mux. Okay, now we will have the mux 4 to 1 mux where there are 4 inputs I0, I1, I2, I3 and one output Q with the select lines A and B. We will write the program for it as follows. Library file behavioral model of mux. Okay, the behavioral model for the mux is library IEEE use IEEE.standardlogic116.all. Now entity start with the keyword entity. We will name this entity as a mux4 and it has 6 input ports bits. Which one? I01, I1, I2, I3, A and B. These are input standard logic. And Q is the output standard logic. And the entity by the name of mux4. Now this entity has been finished. Now for this entity, we are going to write the architecture. The architecture starts with the keyword architecture. Now here what we are going to use, we are going to use the name of the architecture same as the entity. Now this mux4 named the architecture and this mux4 is the name of entity which we have already defined beforehand. Now is signal. Now signal is a local variable. The signal is a local variable designed inside the architecture. You can say the signal is not shown in the diagram. Okay, we are using a local variable in this program. Now cell by the name of cell. Okay, signal's name as a cell and it's a type of integer. Data type is what? Integer for the cell. Begin with the cell selected. Okay, Q will have the input I0 after the 10 nanosecond when cell is 0, having an integer value is a 0. Q will have input I1 after the 10 nanosecond when cell will have value as 1. A similar way, the Q will have I2 as an output after the 10 nanosecond when cell has a 12. Q again will have I3. Q is our output. Q will again have I3 as an input after the 10 nanosecond when cell is having the value integer as a 3. Apart from 0, 1, 2, 3, if there is any other value, okay, then Q output Q will have assigned the value of X. X is undefined. After the 10 nanosecond, when there is a other value other than 0, 1, 2, 3. How to assign the cell value? From where its cell value gets these 0, 1, 2, 3. Now we have to write again a co-occurrence signal co-occurrence statement for cell. Now cell will assign the value 0 when the input select lines A is 0 and logically and B is 0. Else otherwise it will has a 1 value if A is 1 and B is 0. Else if cell has a value of 2 when A is 0, B is 1. Else cell has a value of 3 when A is 1 and B is 1. Cell will have a value of 4 if these 4 statements are false. The end of the mux architecture. Now you can see very easily the writing style of the signal co-occurrence statements. These writing styles show that the architecture has been designed in the behavioral manner. Now you can see this is the functional block diagram of functional table of the mux. Okay, well that means A is 0, B is 0, Q will have I is 0. A is 1, B is 0, Q will have I1. If A is 0, B is 1, Q will have I2. If both are 1, Q will have I3. Further, there is a last value, okay, last value where we have written x. X is an unknown which is assigned to the queue if cell does not have 1, 0, 2, 3. Okay, now there is a simple, again, next topic we are going to cover is the transports and inertial delay. Now, every types of you can say logical gates will need a delay. Inert in the VHDL is a default delay. Inert delay module, the delay oftenly found in a switching circuit. An input value must be stable for a specific pulse period duration of time before the value is allowed to propagate to the output. That is what we call as an inert delay. That means the value of A, for example, let's suppose we will take a buffer. Now this is the example of buffer having the input as A and the output as a B. Now this buffer has a delay of 20 nanoseconds. That means B will have or will assign the value of A after the delay of 20 nanoseconds. Now we will see the graph periodically how time periods flow. Now for the 10 nanoseconds, A remains in the zero state. But after 10 nanoseconds, it transited from 0 to 1. And then for again 10 nanoseconds, it remained in a state 1. But that means throughout the 20 nanoseconds, the A value is not stable. It's changing from 0 to 1. And after 20, it's again changed from 1 to 0. That means the B, that is output, will not have any value since the A does not have a stable state for the 20 nanometers, B will not have the value of A. B will not assign the value of A. So these types of delay is called inert delay. And inert delay can be written as A has been assigned the value of B after 0 nanosecond. That nanosecond we can write, or 10 nanosecond or 20, like that we have a 20 nanoseconds delay. So this statement is commonly known as an inert delay. Even we can use the keyword inertial. That means A will have the value of B using the inert delay after the 20 nanosecond. Then again the next delay what we are going to learn is the transport delay. And transport delay is not a default delay for the VHDL, first thing. Second thing, how it's work. Okay, the transport delay in hardware represent the pure propagation delay. That is, any change in your input is transported to the output, no matter how small or how big it is, or how much transient it is. For example, over here, you can say A will have the value of B after the transport delay of 20 nanoseconds. Now, look at the waveform. A within the 20 nanosecond changes from 0 to 1. And this 0 to 1 transition is shown at B after the 20 nanosecond. You can see that this complete transition you can see in B after the 20 nanosecond. Okay. Here you don't have any clause that the A has to be in a stable state for 20 nanoseconds. It says, rather it says that A will be given to B. That is, B will assign the same value as A, but after the 20 nanoseconds. So this type of mm, delay is called as a transport delay. Okay. Now you can have the transport delay. Now inertial delay modeler, you can see library file IEEE use library standard logic 116 point all entity name by buff is having a in as an input state logic standard logic, B as output standard logic, and of the entity buff architecture name by buff for the entity buff is begin. B will assign the value of A after the 20 nanosecond. So this is what we call inert delay. In a transport delay modules, library IEEE use IEEE standard logic as usual 1164 dot all entity start with the entity keyword for the name of entity delay line is having a port A and B. A is the input logic standard, B is the output logic standard logic, end of the entity delay line. Architecture begin with the keyword architecture named as a delay line for the entity delay line is begin. B will assign the value of A using the transport delay after the 20 nanosecond. That means writing the keyword transport, the delay will change to the transport delay module. In an inert, you need not to write the inert, but in a transport, it is compulsory to write the transport keyword. Okay, and the architecture end with the end architecture name delay line. Now next is one more delay, simulation delta delay. Now this simulation delta delay is are used to order the some types of events during the simulation. For example, we will take this D flip-flop logic. Now here what happened, A input has been inverted into B using the NOT gate or inverter. Now this B and the clock has NANDed and given to the output C. Now C and B both are ANDed and produce the output D. This output D is given to the clock of D flip-flop. DFF, D type of flip-flop. Now how to write and why we need the delta delay, we will explain. Now look at what happens if AND gate give the first result and the NAND is after. AND gate, if AND gate give the first result, okay, that means let's suppose A has a 0 value, A is assigned as a 0 value, automatically inverter will give the value B as a 1. Now this B value is given to two logic gate at the same time. That means to the NAND also and to the AND also. If it happens that AND gate give the first output, then whatever we expecting from NAND will not appear at the AND gate. And if NAND gate, the logic what we are expecting is not should be given the first output as a B, and the B output is should be goes to the NAND gate. NAND gate should produce the output C before the AND gate evaluate the result to D. But what happens if we are not dealing it correctly and AND gate give output before the NAND gate, it will somewhat this table will show you. Let B has been assigned the value of 1 AND get evaluate first. Let's see, C was 1 when AND get evaluate. Automatically D will be 1. Then NAND get result evaluated, and that C which we are taken as a 1 is actual value is 0. Then again AND get has to evaluate and make the value of D as a 0. What if it happen? We will got a faulty result. For that reason, what we are expecting actually, NAND should be given the value first. Matlab, evaluate the inverter. A has to give 0. 0 is converted into the B equal to 1. After B equal to 1, NAND has to evaluate the value as a C equal to 0. When C is equal to 0, then AND gate has to evaluate the value D equal to 0. This is the what we expecting from the logic. But it may happen that AND may give the first value. To avoid such a mess, what we will write? We will write, okay, A having value of not of B. Okay, sorry, I'm writing wrong way. B will assign the value of not logic not of A after some seconds. You can say 0. Let's see. So let's suppose we need for urgent basis. We are not going to give any delay. Okay. So after the 0 nanosecond, or if I even if I not write after the 0 nanosecond, it will be make no problem. Okay. And then C, that is the NAND gate operation. C will have B and the clock signal as a NAND gate. After the 1 nanosecond plus 1 delta second. Then D will have the value of B and C logically AND operation after 1 nanosecond plus 2 delta second. This 2 delta second will provide extra delay, but this delay is very small, infinitesimally small delay. You can't even show on the graph. Okay, it will not make your system more delayed. Okay, so we can use such a logic of delta delay in simulation to give the proper result. Now you can see if we use delta delay, let's suppose for the 10 nanosecond, A is equal to 0, the inverter evaluate and give the result B is equal to 1. Then this B is equal to 1 given to the NAND gate and AND gate. The NAND gate reply first, since we have kept NAND gate delta delay as a 1 delay and 1 nanoseconds. Okay, NAND gate reply first. Okay, AND gate has more delay, so it will wait. The NAND gate reply first and give the output as a C equal to 0. This C is equal to 0 is given to the AND gate, and now AND gate evaluate the result as a D equal to 0. This whole operation is done within a 1 nanosecond, and that is much smaller value to work on. Okay, now you can see B, A will have, okay, this was the something different way. Hmm. Hmm. Now, entity RGA clock input, D clock output. Entity signal B and C is the signal local variable for the architecture test for the entity RG. Now begin. B is not of A with the notice no delay. C is not of clock and B, that is the NAND operation. D will have C and B tested in. Okay. The next topic what we are going to cover is the drivers. Okay. Now, any output may drive from the two signal. Okay. For example, see this architecture test for entity task begin. A is the output B driven by assigned by the signal B after the 10 nanosecond, and the same output A has been assigned the value of C. That means signal A has a two driver B and C. Signal A is being driving from the two sources B and C, and both are after 10 nanosecond. Okay. Each co-current signal assessment create a driver for a signal. Every this will create one driver, this will create another driver. Okay, na? The first statement create a driver that contain the value of signal B delayed by 10 nanosecond. The second statement create a driver that contain the value of C after the 10 nanosecond. However, now, how these two drivers are resolved to left to the designer, it depends upon the VHDL programmer. You can give a delay for the behavior. Okay, wait, call again. Huh, huh. Now, what are the bad type of driver module? Now, this is the bad driver. You can see from the above. Okay. Now, use workload standard 1164.l all. Now, entity by the name of Mux been designed and the architecture bad for the Mux is been designed. Here what you see, the output Q will have input when A is 0, B is 0, else is 0. Okay, now this else 0 is a bad driver. Okay, and then again it has a value of I when A is 1, B is 0, else is 0. These model design where I0 is to Q when A is 0 equal to A0, B is equal to A0, I1 equal to when I equal to you can say beforehand we have make a local variable cell, and that local variable cell decide A and B values and given to the output Q. The better way writing is to create only one driver for a signal Q as shown below. Okay. Now Q will have the value of input I0 when A is 0, B is 0, else it will have I1 value when A is 1, B is 0, else it will have I2 value when A is 0, B is 1, else. Or if all are false, it has X value. It's a better way. The best is what using the local signal variable, that is we have used as a cell. The next term is the generic. The generic are the general mechanism used to pass the information to instantly to of an entity. Okay. An example of generic is given here. The following is the example of entity K that has a 3 generic associated with it. Okay, entity by the name of AND2 has a generic rise, falls, time. Okay, sorry, rise and falls are the time and the load is the integer time. So this is what it has 3 generic. Now this entity allows the designer to pass a value of rise and fall, delay, as well as a loading that the device has its output. Now you can see the architecture, okay, for the AND2 entity which has been designed it. Okay, now C will have internal in rise plus load time of 2 nanosecond when internal is 1, else internal after 2 falls load time is 3 nanosecond loaded to the load dependent. Okay, now this local signal in turn is a bit type, we have defined it. Okay, to store the value of expression A and B. The generic rise, falls and load contain the value that are passed in by component instantiation statement. Initialization instantiation. Let's just look the piece of the next look. Okay, that is onto the total this shows. Okay, that is enough for the generic. Block statement. Mm, block statement. Block statement. What is that?